Greetings and welcome to the second part of your lecture 8 of Tripoli 23. To pick up where we left off with the considering the torque on a very small rectangular or a square loop as shown in the figure in front of you. Okay, you have since the square loop is very small, the magnetic field is assumed to be uniform. Okay, and we can solve the net torque that is acting on the square loop. Okay, so I won't run through with the solution, but it turns out that the torque is equal to this quantity right here, the current multiplied to the area enclosed by the square loop, differential area because it's very small, cross the magnetic field that is acting on it. Okay, so ds is your differential area, okay, differential area vector, okay, and we can define this IDS right here as what we call the magnetic dipole moment. Okay, so recall your electric dipole moment. So it was defined when we have two charges, okay, 2-point charges that are separated from each other but cannot pull away from each other because of internal forces. For example, within an atom, okay, because of internal forces within the atom, the uh, the positive charge and the negative charge uh, cannot pull away from each other, creating some pole between them that is polarized. Okay, has a small voltage difference or potential difference, but they just can't seem to pull away from each other. Okay? And this is your electric dipole moment. Okay? So your magnetic dipole moment, in contrast, it results from a current that is spinning around a very small area. Okay? The direction of the magnetic uh, dipole moment is perpendicular to the area, right, defined by the right-hand rule, as you can see here. If you curl your hand to the direction of the current, where your thumb is pointing, that's where the direction of the dipole moment is. Okay? And this is the source of the magnetization of our materials. Recall that for our if you have electric field, if you have an electric field on our materials, uh, polarization is imminent. Okay? If there is no current that can flow within the material, like this, we have a dipole, electric dipole. Similarly, if we have a magnetic field, you have a magnetic dipole, and magnetization can occur. So, where can we find this magnetic dipole moment? Well, we can find them within our atoms. Right? The source of magnetization is primarily due to three sources. We have the orbital spin of electrons, or their electrons revolving around the nucleus. And we have the rotation of the electron about its own axis. Right? So these are the quantities of the magnetic moment. Okay. So the orbital magnetic moment is dependent on the distance of the electron from the nucleus. The more electrons, the more spin. Okay. And the electron is rotating by itself. Its magnetic moment is defined by this equation right here. And also, we have the nucleus spinning around its own axis. Since the nucleus is positively charged, it can also have its own magnetic moment. However, the nucleus spin is very slow, since it's more massive, much more massive than your electron. So therefore, it becomes negligible. Right? And all of our materials actually have a dipole moment, magnetic dipole moment. Okay. So what happens if we apply a magnetic field on our materials? Okay? So that is the process of magnetization. Okay? So let's just recall the definition of our magnetic dipole moment. We have a current that is spinning around a differential area. That's your bound current. The vector m, which is perpendicular to the area and whose direction is defined by the right-hand rule, is the magnetic dipole moment. The magnetic dipole moment, therefore, is your bound current multiplied to your differential area. Right? The total, so this is just for a single atom, the total magnetic moment found in a very small volume where you have a lot of atoms, let's say n atoms, the total magnetic dipole moment is this. Right? The sum of the individual magnetic dipole moments of each. This should be a vector sum. Okay? So n here is the number of magnetic dipoles. So it can be illustrated by this. So this is just a total magnetic moment. Okay? The magnetization is different. You let this very small volume approach zero. And that is your magnetization. And this is what happens. So this is an illustration of what happens when we apply a magnetic field to a material. Okay? If you have an external magnetic field, so the external magnetic field will actually force all these individual magnetic dipole moments to align to that magnetic field. Align approximately to the magnetic field. Right? So it forces the magnetic moments to align each other, therefore creating a more powerful magnetic field. Okay? The individual magnetic fields of each magnetic dipole moment will add up, okay? And the result is your magnetic field within the material becomes powerful, okay? Or basically stronger, okay? So this is when the realignment occurs. So let's just review a little bit. Let's backtrack. If we look at the dielectric, okay, there's the existence of electric dipoles. Right? If we apply an electric field in this direction, right, the positive charges will actually be attracted to uh, the positive charges will actually go towards where the electric field is heading, and the negative charges will go the opposite direction. And the electric dipoles will realign with each other. What happens here? The electric flux actually increases. The electric flux increases. Right? Similarly to our magnetic field here, for a linear isotropic media, okay, so remember the definition of isotropic. Okay, so a resulting magnetization is actually a scalar multiple of the applied magnetic field. Okay, similar to our electric flux here. So the polarization, okay, remember from your electric field, the polarization is equal to some constant chi e multiplied to your electric field intensity. It's similar to our magnetic field. The magnetization here is a scalar factor of your magnetic field intensity. And this magnetization adds up to the flux that is inside the material. Therefore, the total flux is equal to mu naught multiplied to H plus M. Okay? So the magnetic flux is multiplied, uh, sorry, the magnetic flux is equal to the total magnetic field intensity plus the magnetization multiplied by mu sub 0. Okay? And substitute the first equation, you get this expression right here. We can factor out H and we can redefine the factor inside. That is your relative permeability. Okay? So recall that for our electric flux, it becomes epsilon E. This is your relative permittivity. And this mu R right here is your relative permeability, which is equal to 1 plus the magnetic susceptibility. Take note that it's 1 plus some value. Right? So this chi m right here actually is almost always greater than zero, but there are cases that it's not. Right? Unlike our dielectric, so if you apply an electric field inside a dielectric, the electric flux absolutely increases, but for our magnetic field, it's not always the case. But let's see. Okay. So basically, in general, excuse me, in general, the magnetic flux density is equal to mu, the permeability of the material, multiplied to H, which is the magnetic field applied inside the material. Okay. Now recall for our electric field, we considered three types of materials: conductor, semiconductor, and our uh, dielectric. Okay. For our magnetic materials, there are three types. There are three types of magnetic materials, and I think you've already heard them from your elementary or high school science. Okay. But let's describe them in terms of when we apply an external magnetic field inside those materials. You have diamagnetic, paramagnetic, and ferromagnetic. Diamagnetic materials basically have a if you apply a magnetic field in our diamagnetic materials, well, the net magnetization is actually opposite in the direction. Okay? So the net magnetization is opposite the direction of the external electric field. If this is your external, the external, the magnetization is this way. Okay? However, it's very small. It's less than 1, but very close to 1. Maybe we can actually just ignore it because it's negligible. Now, if you remove the external magnetic field, there's no magnetization remaining inside the diamagnetic material. Basically, it just restores to its original state. Paramagnetic materials, on the other hand, okay, initially the spin and the orbit components do not completely cancel each other out, but the magnetic moment from atom to atom is randomized. Okay? So basically, instead of for that diamagnetic, it's different. For each atom, the magnetic moment is zero. Okay? But for paramagnetic materials, it's there has a net magnetic moment for each atom. However, okay, however, since each atom, the magnetic moment has a different direction, okay, something like this, okay, maybe something like this. It's very random. The net magnetization initially is zero. Okay? But when we apply an external magnetic field, the dipoles align with each other, creating a stronger magnetic flux inside the material, or positive chi-m. Therefore, we have a relative permeability that is greater than 1, but it's close to 1. But when you remove the external magnetic field, the magnetization remains. Okay? So let me try to illustrate that. For diamagnetic materials, there are atoms, okay, inside the material. However, each atom do not have a magnetic moment, individual magnetic dipole moment rather. But for paramagnetic materials, each individual atom has a net magnetic moment. However, the direction of the magnetic moment is all randomized. Therefore, they cancel each other out, leaving no net magnetization. Kind of looks like this. Okay? Random. The directions are random, therefore there's no magnetization initially. Okay? The third one is the ferromagnetic material. So this is the most interesting one out of the three, mainly because the dipole moments are very large individually. So individually, you have very large dipole moments, and for a group of atoms near each other, they are aligned, okay, creating a bigger dipole moment that's aligned like this. Okay? And there are several of them. There are several of them. However, the several domains, okay, domains as you can see, the several domains have a different direction in terms of spin. Okay? So they have different directions, therefore there is no net magnetization at the start. But if you apply an external magnetic field, they will be aligned, giving a bigger boost in your magnetic flux inside the material. And finally, when you remove the external magnetic field, there is a magnetization remaining inside the ferromagnetic material. This is actually how the magnets are charged. So you kind of like charge the magnets inside to retain the magnetization inside your magnet. And this is what you see commonly, your horseshoe magnet, your ref magnets, etc., etc. The magnets that are spherical and very small but very strong. You can create structures with them. Yeah, those are ferromagnetic materials. Okay? There are also other magnetic materials. Okay, and they won't be discussed here. Okay, we'll just look at the three: ferromagnetic, paramagnetic, and diamagnetic. Other categories include ferrimagnetic and anti-ferrimagnetic materials. Okay, so to summarize all three, okay, you have three different types of magnetism or three different types of magnetic materials. Okay, when you have an external magnetic field applied to each of them, the dipole moments for the diamagnetic material will align in the opposite direction, but it's very small. If you remove this, well, there's no magnetization that remains. For your paramagnetic material, if you apply an external magnetic field, your your individual magnetic dipole moments will align with the external magnetic field like this, like creating a stronger magnetic flux inside the material. But if you remove the external magnetic field, well, there is no magnetization that remains inside the material. And finally, if you have a ferromagnet, you apply an external magnetic field, and create a stronger, excuse me, create uh, a stronger magnetic field or magnetic flux inside the material as compared to a paramagnetism. Okay? And if you remove the external magnetic field, there's a large magnetization that remains inside the material. And it can still attract other magnets or repel them. Okay? Okay, with this in mind, what if you encounter a boundary? So similar to your electric field, what if you encounter a boundary? So you recall your electric field, encounter a boundary, what happens to the uh, electric field intensity, electric flux density, etc., etc. Right? So let's look at that. So we have two materials. In material 1, we know the direction of the magnetic field. In material 2, we don't know where it's heading. So what happens when we have a magnetic field that is, if I have a magnetic field that's entering a boundary? So first, we decompose the magnetic field, both flux density and field intensity, into its normal and tangential components again. Mainly because if you enter a surface, you can actually decompose any vector into two components, namely normal and tangential. Let me change the color of the pen. Okay. So how do we solve for the relationship between the magnetic field in material 1 and material 2? We will use what we have learned so far. First is applying Gauss law for magnetism. So that is for your normal components. If a normal component here enters the surface, so we let a very small closed surface set the height such that it's very small. So that means the magnetic field will only be considering is the one that is normal. Okay? There's a magnetic field entering and there's a magnetic field leaving. Okay? If you get the closed, okay. If if you get the closed surface integral of your magnetic field, so according to Gauss' law, the closed surface integral of a magnetic field is equal to 0. Why is that? There's no such thing as a magnetic dipole. Right? Therefore, if we try to enclose a magnetic field, if we try to enclose, there will always be a north and south component to the magnetic field. Okay? There will always be a north and south component to the magnetic field. All right. With that in mind, if we have this set up right here, we can see that the normal components are actually equal to each other. Okay? The normal components are equal to each other. If you recall your electric field intensity or electric flux density, the difference between the flux going out minus the flux going in is equal to the charge distribution in the boundary. But since there's no magnetic charge inside the boundary, that means the normal components of the flux, magnetic flux density, should be equal to the one going out. What's going in goes out. Now, if you look at the tangential component of the magnetic field, let's apply Ampere's law. Set the loop such that this height right here, is approximately 0 or very small. Okay? And the tangent components are in the same direction with each other, ht1 and ht2. Okay? Let's set the direction of the loop to be, okay, since the current going into the page, the direction of the loop is defined by the right hand rule. Okay? So ht1 dotted to this vector right here, that's positive, and ht2 dotted to this vector going the opposite direction is negative. So that, and the length of both sides is delta L. That's why we have this expression right here. That is equal to the current density, which is a sheet current, multiplied by the length of the path. Okay? K delta L. If we divide it by delta L, we can see that the magnitude of ht1 minus the magnitude of ht2 is actually equal to the current density, okay, the sheet current density that is moving inside. Okay? But in terms of vectors, okay, we look at the normal component between on the surface right here. So we're looking at the normal component AN12. Okay? So this is the normal component to the surface. Let me try to. Where's the eraser? There you go. AN12 here actually is the normal component from here to here. The normal component of the field that goes from the second, uh, the normal component of the field that goes from the HT2 to HT1. Okay. Wait, sorry. It's a different, no, no, no. It's from HT1 to HT2. Okay? HT1 to HT2. Okay, so this is the direction of AN12. Alright? So this, to summarize, wait, sorry, this is not the summary. Okay, so for example, if we have two materials with different relative permeabilities, we have mu1 right here and mu2 right here. Okay. Given that B1 is this and K between in the boundary is equal to this 80 AX hat, okay, solve for B2. So basically just need to apply the definitions or the if you forgot the relationship of the boundary conditions, well, you can just apply Gauss law and Ampere's law. Okay. So the normal component, okay, of this material right here, the normal component is just AZ hat. Okay? So the AZ hat component of B1 is equal to the AZ hat component also of Bn2. And that means Bn2 is equal to positive 1 AZ hat. There you go. Something like this. The tangential component is what is left. So just remove the AZ hat and you have your tangential component. Okay? So that's the tangential component on material 1. And from there, you solve for the tangential magnetic field intensity just by dividing mu1, which is the the permeability of the material. So you divide that, you get this, okay? And apply the boundary condition for tangential components. You get HT1 minus HT2 is equal to AN12 cross K hat, okay? So solve for HT2, just need to transpose this and then transpose this back here. Okay. So HT1 is 500 AX hat minus 750 AY hat minus, okay, the direction from 1 to 2. So the direction from 1 to 2 is negative AZ hat, as you can see here. Okay, and AZ hat cross AX hat, negative AZ hat cross AX hat is AZ hat cross AX hat is AY hat, and you have a double negative here, it becomes positive. And finally, we have the magnetic field intensity at material 2. The tangential component is equal to this. And here, from here, you can solve for the tangential magnetic flux density by multiplying mu sub 2. So you get this expression for BT2. And you can solve for the total magnetic flux density, which is the tangential plus its normal component, and you get this expression right here. And that is the end of the part 2 of your lecture 8. If you have any questions, do not hesitate to leave a comment below. I will answer as soon as I can. I'll always be active on and always try to be online as much as possible. Okay, that's my time. See you next meeting.